Okay, so let's continue. Uh, like maybe I would just give a quick recap of like what we have seen before the break. So we started with so basically like we started with the regular expected prediction error that we have, right? Like expectation with respect to the data, like loss of y comma h of x, and we expanded it and we tried to decompose this loss into two terms, right? So we had in the end of like our discussion, like so we divided it into two terms. So the first term is going to go to 0 when h of x is equal to e of y given x, which is the true regression function, right? And on the other hand, we have the second term, which is just the variance of y given x, and it has nothing to do with h of x. And this is what we call as irreducible error for that particular problem. Okay, so now let's take the first term and like further divide this into like two more terms. Okay, so now we are going to consider h of x minus e of y given x the whole square. Okay, so in practice, we don't have access to the true distribution, so it's going to be very hard to find a h of x which is exactly e of y given x, right? So we are replacing that with empirical risk minimization, and usually in empirical risk minimization, you're going to have a data set D, okay, which contains a finite number, let's say n, of data points. Instead of considering this entire distribution of data, like we are considering this one specific data set which has n data points. Okay, so to highlight the fact that the hypothesis is learned from the data, so we are going to call h as h of x given the data. Okay, instead of just calling h of x, we are going to call that as h of x given the data. Okay, so now the loss becomes h of x given the data minus e of y given x the whole square. Okay, so now there are many possible data sets from one distribution, right? Like, so let's say I have a distribution of like data, like I could sample 100 data points, that becomes one data set 1. I could sample another 100 data points, that becomes data set 2. I could sample another 1,000 data points, and that becomes data set 3, and so on, right? So we could have many data sets. So now comes the question of what would be the performance of this model on an average for different types of data sets that we could consider, right? So we are going to ask, what is the expectation with respect to D for this particular error? Okay, again, I'm going to add and subtract a term. So basically, I'm going to do ed h of x given the data set minus expected h of x given d plus expected h of x given d minus e of y given x the whole square. So I have just added and subtracted the second and third term, like which are same, right? So they are still, left hand side is still same as the right hand side. So we will do the same process here. So we'll consider this as A, we'll consider this as B. So it's A plus B the whole square, right? So now this becomes expectation with respect to D, h of x given D minus expected h of x given D, the whole square, plus expected h of x given D minus expected y given x the whole square, okay, plus twice, okay, instead of writing the whole thing, I'm going to call this as A, call this as B, and say 2AB. Okay, so now we could do the same exercise if we want to do it again, like, but we are not going to do that. So this term is going to be 0. And I will leave that as an exercise. Okay, so when you do the 2ab, it's going to be 0. So we just need to consider the first and second term. Okay, so let me cut paste the first and second term. Okay. Okay, so what do we have? The first term, okay, is that right? Yeah, I think they are same. So now if you look at something is wrong. No, I think they're fine. Okay, so so if you look at the, okay, sorry, I'm just not sure if I did anything mistake in the notes. Okay. Let's go back. Okay, so maybe, okay, so I think I missed bringing the expectations inside in the notes. I will fix it in the notes. But if you look at the second term, it is basically expected h of x given d minus e of y given x, the whole square, okay? And the first term should be expected h of x given d minus e of d, h of x given d, the whole square. Okay, so now this, like, we're going to call the first term as the bias of the model. In some sense, it's a bias square, okay? And the second term as the variance, okay? So now why do I call the first term to be the bias, right? So remember that this is the true solution, like the optimal solution, right? Now, what does this term means? This term means what would be the expected H function that I could get from this model, right? Like where the expectation is over all possible data sets. In some sense, this is the average solution where the average is taken over multiple data sets. Okay, so now the difference between the optimal function and the average solution of your model is exactly the bias of the model. So because this model is biased, the optimal solution, like the average solution of this model is not going to be the same as the optimal solution. There is a gap, and this gap is captured by the bias. Okay, now let's look at the variance term. So what does the variance term says? This says that this is basically the difference or the gap between the average solution and one specific solution for a data set. So now for one possible data set, I have a H, and how far is this H from the expected H or the average H for this particular model? Okay, so now that is variance. So maybe let me try to like explain what is bias and variance like in plain English. So what is bias? Bias is basically the extent to which the average prediction over all data sets vary around the, let's just say H star. Okay, so the extent to which the average prediction over all possible like data sets vary around the H star. Now similarly, variance is given by extent to which the solution for individual data set vary around the average. Okay, or in other words, variance tells us how sensitive is h of x comma d for a particular data set D. If the model is very sensitive to the data set, then the variance of the model is high. If the model is less sensitive to the data set, then the variance of the model is low. Okay, so to recap what we have seen so far, we started this lecture with the expected loss, right? And we have decomposed this expected loss into 3 terms. In fact, so the first term was bias square, then the variance, then the noise. Okay, so we have an equation for all these terms. The bias square, right, is given by integral expected h of xd minus e of y given x okay, maybe I'll just copy so that it's easier. Minus e of y given x, the whole square, p of x dx, right? And the variance is given by integral expected h of xd minus the expected, like the average solution, p of x dx, right? And similarly, the noise is given by simply the variance, e of y given x minus y, the whole square, p of x comma y dx dy. Okay, so it doesn't matter like if like if you don't get these 3 equations, but let's summarize the entire discussion about empirical risk minimization in a cartoon. Okay, so normally for any problem in hand, you have a set of possible hypotheses. Okay, so let's call this as H. So you have all possible hypotheses, like which could take X as input and make prediction Y, right? So now when you do model-based learning, so you have a specific model F, right? Now for every possible W, this F represents a hypothesis. And now just because this model has some inductive bias, like it's going to restrict the class of hypothesis that you could consider, right? So now the restricted class could be something like this. Okay, so now in reality, there are many possible situations. Like, so let's say, for example, the true function, the source function that you are interested in is outside this h dash. Okay, so for example, let's consider this dot is my source. Okay, so now this dot represents the source distribution from which we are sampling x and y. Okay, now we have learned in the in the last few lectures that the true solution E of y given x can never be, so basically you can never find the true source simply because of the noise, right? So there is already the gap in this solution because of the noise, right? So now this is the first gap, right? Like, so even if you find E of y given x, you're going to have some error, right? Like, so that error is the base error rate for classification. And so basically this is unavoidable. So now let's consider the solution that we are going to get from this restricted H dash, right? So now we will talk about, first we will talk about the average solution. The average solution, let's say, is here. So this is expectation with respect to the data set H of x given D. Okay, so now you can see that there is a gap between the average solution by this model and the optimal function e of y given x, right? So now this gap is because of the bias. Okay. Now there is a next step of approximation. So we don't have access to the distribution, entire distribution, right? Like we only have access to one specific data set. So now depending on which data set you are using, you could get this solution or this solution or this solution or this solution or this solution, right? So now let's consider this particular solution, the black dot in the bottom, right? Now you can see that there's actually a gap in performance between this specific solution and the average solution. Okay, so now this is the third level of gap, right? Like, so now this gap is because of the variance in the data set. Is that clear? So in some sense, when you see some error from your model, this error is composed of three different sources of errors, which are noise, bias, and variance. Okay. Now there are ways to deal with the error due to bias, error due to variance, but there is no way to deal with error due to noise. So this is the irreducible component, right? Like, so now this is irreducible. And what is reducible is these kind of errors. And there is always a trade-off between bias and variance. Okay, so if you have like in the case of very flexible models, like let's say k nearest neighbor, right? So those models will have low bias but high variance. Okay, so now to deal with such models, you need to add more data points so that the D becomes bigger, and like, so you can try to reduce the variance, right? And on the other hand, we have very rigid models like linear regression, for example. In the case of linear regression, it cannot learn a nonlinear boundary, right? It's always a linear regression function. Now this model has a very high bias but low variance. That's because the model is simple, it has low variance. Okay, so now we can kind of illustrate this by this graph. So the x-axis here is going to be the complexity of the model. Okay, so sorry. So the x-axis here is the complexity of the model. So as you get into more and more, Masood, let me just finish this and I will let you speak. Okay, so x-axis here is the complexity of the model. As you, like, we started with like one k-nearest neighbor and linear regression, but we are going to discuss many more models in this lecture, like in this course. And as you go for more and more complex models, the bias of the model is going to reduce. Okay. On the other hand, the variance is going to increase. Okay. Now, remember that the error is a sum of these two things. So there is an optimal point. So there is this, okay, maybe I'll use a different color. So there is this point where your true risk, this is the representation of your true risk. So there is an optimal, there is an optimal complexity for the model, and that would be the model with the minimum risk possible, right? Like, but in reality, it is very hard to find the right model for the right task in hand. Okay, so to help us find a right model, like there are many discussions in the literature. Like, so one of the commonly quoted hypothesis is what is known as Occam's razor. So, which basically says that one should not increase beyond what is necessary the number of entities required to explain anything. So another way to put this is, if you have two models with different complexity, and same generalization performance, you should prefer the simpler model, okay? Or in other words, seek the simplest explanation. Okay, so Remy, can you unmute Masood?
Sorry, just a question. Based on the slide, the variance and bias, previous slide. Sorry, would you please?
Yeah.
Yes, exactly. So, is it true to say the variance is a function of bias also?
Variance is a function of?
I mean, they are not independent from each other.
Oh yeah, they are not independent of each other. There is a trade-off. That's why there's a trade-off, right? Like, so there is always this like kind of tension between both. Like, so you go for highly biased models, the variance is going to reduce. You go for like less biased models, variance is going to increase.
Thank you.
Okay, so yeah. So any other questions? Okay, so now let's actually look at the bias variance in the simple regression example that we have been using as a running example in this course, right? So let's go back to the regression example, which is the sine wave prediction, right? So now in this case, I'm going to create 100 different data sets, okay? Each containing n is equal to 25 data points from sine of 2 pi x curve. So remember the sine pi problem. So if we're going to take the sine data set problem, and like I'm going to generate 100 data sets with 25 data points. Okay. So in this case, L, the total number of data sets is equal to 100 and N is equal to 25. Okay. Now my model, the regression model that I'm going to consider is a basis function regression model. So I'm going to consider a regression model with Gaussian basis function. And specifically, I'm going to consider a model which has 24 Gaussian basis functions, okay? So the reason is because now this has 25 parameters, so I can easily overfit to these 25 data points, right? So now this is my setup, okay? So now you can actually see like how, like, like for different values of lambda in L2 regularization, the solutions look like. Okay, so in this case, the top is lambda, which is large. So when you have a larger lambda, you are aggressively regularizing, right? So in this case, the bias is going to be high. You're highly biased towards solutions which has smaller magnitude, okay? And the variance is going to be low, okay? So which is also visible from the left-hand side. So the left-hand side is 100 different functions that I have fitted for 100 different data sets. And you can see that all these functions are very close to each other, right? And you, on the other hand, you could see the average of those 100 functions in the right-hand side. And that red line doesn't look same as the sine function, right? So the problem with like having highly biased model is like you might reduce the variance, but the model becomes biased in such a way that it might not learn the proper solution. Okay, so in the bottom, you see that lambda is very small, right? Which means the bias is low, but variance is high. Okay, so you can see that every curve is looking different, right? Like there's a variance, there's a huge variance between these 100 curves in the left-hand side, but the average curve looks somewhat similar to the sine function, right? Sorry, just give me 1 second. Okay, sorry for that. Now in the middle, you have some solution which is in between both the bias and the weight, like in between like large lambda and small lambda. So like the function looks, the average function looks almost same as the true function. Okay, so now in this case, we could actually compute the average prediction, the bias, and the variance for this specific regression example, simply because we have access to the true function for the synthetic data set, right? So the average prediction, let's call it as h dash of x, is simply average over all the 100 h functions that I have. So summation over L is equal to 1 to L, h L of x, 1 over L. Okay. Now the bias term is given by 1 over n, summation over I is equal to 1 to n. This is the average prediction. And what is the gap between the average prediction and the true function? True regression function, right? So now remember that normally you cannot compute this second term, but in this particular synthetic example, since we created the data set, they can compute this. So similarly, the variance is given by 1 over n, summation over I is equal to 1 to n. 1 over L, summation over L is equal to 1 to L. H L of xn minus h bar of xn. Okay, so we could compute all these three terms, and this is how the graph looks like. So in this case, you could see that as like you increase, okay, so basically as you increase the value of lambda, the bias is increasing. You could see that the blue line is increasing, right? And similarly, the corresponding variance, the red line, is decreasing, right? And the bias square plus variance is the summation of these two things, and that looks exactly correlated to the test error. Is that clear? Okay, so now to summarize what we have seen so far, so there are three important concepts. One is true risk, okay, which is what we care about, but in practice we can never compute this. So we often compute the empirical risk, okay, and there is also this overfitting that we have discussed several times. Okay, so now let's find the relationship between these three terminologies. Okay, so now the x-axis here is again the complexity of the model. Okay, so as you increase the complexity of the model, you could fit any data set, right? So the empirical risk would go to 0. So this is the empirical risk. Okay, but that is not the case with true risk. So the true risk will reduce up to some point, right? Then you might start overfitting and the true risk increases. Okay, so now this region, right, where the true risk is not minimum but decreasing, is the underfitting region. And this region where the true risk has started increasing is the overfitting region. And normally you have this one specific configuration for the best model. So when you are dealing with a model which is to the left of this, then you are underfitting. If you're dealing with something to the right of this, then you're overfitting. Okay, so okay, so that is the discussion about empirical risk minimization. So maybe I will take a couple of questions before we move on to like discussing classification in detail. Okay, so if you guys have not noticed, for most of your simple questions in chat, the TAs are answering them there. So So if you are wondering that there is no question raised, but that's also because the TAs are answering all the questions. Okay, so Krunal.
Can you explain again why would empirical risk go down all the way to 0?
Okay, so what is empirical risk? So empirical risk is basically the loss with respect to the data set, right? So it's 1 over n summation over I is equal to 1 to n, the loss of, let's say, y of I, h of x of I, right? Now, let's say I have 100 data points, n is equal to 100. We have already seen this in regression, right? Like if I have 100 data points and I have so in some sense we could define the complexity in terms of the number of parameters, right? Like so for example, like if I use a linear regression model with 10 parameters, the empirical risk cannot go to 0. But if I use a linear regression model with 100 parameters, then the empirical risk could go to 0. It is exactly 0 when you have 100 parameters, right? But because when you have 100 parameters and only 100 examples, you could fit all those 100 examples perfectly. So anything above 100 parameters, like you are overfitting, empirical risk is 0, but the true risk is maximum.
Okay.
Okay. There's a question in chat. Is the empirical risk like the training MSE and true risk the validation MSE? No. Empirical risk is the training MSE. That is correct. But the validation MSE is an approximation of the true risk. So you can never compute true risk simply because you don't have access to the true distribution. But the training MSE is exactly the empirical risk. Okay, that is a good, these are good questions. Anything else? Okay, so let's move on. Okay, so one thing that I'm still figuring out with this course is we have 2 hours and 1 hour. Like, so usually like my preparation was for like 1.5 hours. So that is one reason why like we start something in one lecture and then like continue that in the next lecture. But my general advice is like, please do a quick review of the previous lecture before coming for every lecture so that you feel the continuity. We are revising in the class, but still it's better like if you just, it's more important for like reviewing the previous lecture notes than the current lecture notes. Okay, so now we have spent so much time in this course on regression, right? So from now on, like we are going to focus more on classification. Probably we will come back to regression like towards the end. But for the rest of the course, like we will focus more on classification. Okay, so today, like we will just get started with some basic notations, which will help us like set stage for learning like more classification algorithms in the future lectures. Okay, so now let's consider a K-class classification problem. Okay, so the classes are given by C1 to CK. Okay, so there are actually 2 stages in this classification. Okay, so the first stage is what we will call as inference stage. In the case of inference stage, we will use the training data to learn a model for P of CK given X. So we will first learn a model for the probability of choosing a class given the input. Okay, so once you have this particular probability distribution, then you have the decision stage. So the decision stage is simply to use these posterior probabilities to make optimal class assignments. Okay, so this is where the statistical decision theory that we learned come into place, right? Like so the C hat of X is given by arg min over all possible classes, summation over k is equal to 1 to k, loss probability of ck given x is equal to x, right? So we have already seen this in like a couple of lectures back. So this loss is basically the price for classifying an observation belonging to class ck to class C, right? So we have also discussed about 0-1 loss functions. Remember that like you have a matrix of 1 to k, where the diagonal is 0, because if you correctly classify, you get 0 loss, and the rest are 1, right? So when you have 0-1 loss function, the C hat of x is given by R min of C belonging to C, 1 minus probability of C given x is equal to x. So this is just a recap of like what we have already seen before. And this is also equivalent to R max of probability of C given x is equal to x, right? So we had a name for this particular classifier. This is basically the base classifier, right? So basically what we are doing here is, if the loss is 0-1, then once you have P of ck given x, all you have to do is pick the class which has the maximum probability, right? It's a very intuitive thing, and that is what the decision theory is also asking us to do. Okay, so now this is the basic setup, right? Like, so now similar to how there is a true function in regression and we can never like find it, like, and like we need to resort to model-based techniques. The same holds for classification too. So we could never find this base classifier simply because we don't have access to the true probability distribution. So we are going to come up with our own models which are going to estimate these probability distributions. Okay, so now there are at least 3 approaches to solve classification problems. Okay, so for today's lecture, like we would just try to go through these 3 types of solutions, but we are going to see example algorithms for every class, like for every approach in the next few lectures. Okay, so the first approach is to find, basically the first approach is to model the class conditional distributions, densities, P of x given ck for each class ck individually. Also, you infer the prior class probabilities P of ck. So this is the first solution. Like, so you first try to model P of x given ck, also model P of ck. So once you have these 2 terms, then you can use Bayes' theorem to find P of ck given x. So P of ck given x is given by P of x given ck, P of ck divided by P of x. Okay, so now this is known as the posterior class probability, and the P of ck is the prior class probability. Okay, and the P of x is, you could expand P of x as summation over k, P of x given ck, P of ck, if you want. Okay, so now this is the first approach. So you first model P of x given ck, P of ck, and then use Bayes' theorem to find the class. Okay, so there are a couple of ways to do this. So like one option is to actually, so instead of learning these 2 things separately, you could also learn P of x given ck directly, and then you normalize this to obtain P of ck given x. Okay, so once you find P of ck given x, then you can use the decision theory to choose the example, choose the correct class. Okay, so now this approach is known as generative model. So we are going to call this as generative model simply because this class of solutions care more about the joint distribution P of x given Ck, because once you have this joint distribution, then you can actually use this joint distribution to sample any number of data sets that you want, right? Like similarly, once you have these two things, P of x given Ck and P of Ck, you could sample the data set like by basically sampling the class first and then condition on the class you sample the x, right? So this is called generative model simply because like you can generate data from this model. Okay, now that is the first approach, right? So now the second approach is a bit simpler than the first approach. So why do we need to go through this whole process of finding P of x given Ck, P of Ck, and then invert it by using the Bayes theorem, right? So instead, the second class of solutions, they directly model P of Ck given x. So you directly model this. There is no Bayes rule, no P of x given Ck, no P of Ck. Okay, so like you directly try to come up with a model which will, given x, try to predict P of Ck given x. Okay, now this is known as discriminative model. Okay, because given x, it just tries to discriminate this x between one of the k classes. Okay, now there is an even simpler approach to do classification, which is basically directly find a function f of x, which maps x to class label. Okay, so now in this case, we are going to call this f of x as a discriminant function. And there's no probability here. Okay, we are going to call these models as discriminant based models. Okay, so there is a spectrum of solutions actually. Like in one end, you have pure probabilistic models, right? Like, so you have generative models where the idea is to compute either P of x given x comma Ck or P of Ck and P of x given Ck, and then use Bayes rule, right? In the middle, you have discriminative models, which are directly trying to model P of Ck given x, okay? And in the other end, you have discriminant based models where you're just learning some f of x, like some function, which doesn't even need to be like a probabilistic value, okay? Okay, so we are going to see an example for all these three in the future. But to begin with, like we would focus more on linear classification. Okay, so now let's consider a simple two-class problem. I have two features, x1 and x2, and I have data set of circles and crosses. Okay, so let's say this is one class and this is another class. Okay, so now if I have to classify between these two, then I need to draw a decision boundary separating these two classes, right? So in this case, I can actually draw a line which perfectly separates these two classes. Okay, now this line is what we will call as the decision boundary or decision surface. Okay, so let's consider x to be class 1, circle to be class 2. Okay, so now the region which is to the right of this red line, right? So this region is the decision region for class C1. Okay, now similarly, this region is the decision region for class C2. Okay, so we have discussed a lot about linear models. so far in this course, right? Like we will actually see a few more linear models before we move to nonlinear models. So in the case of linear models, the decision surfaces are linear functions of the input vector x, okay? And hence they are actually defined by a d minus 1 dimensional hyperplane with d-dimensional x. So in this case, I have a 2-dimensional feature space, right? So the linear decision boundary is 1-dimensional, so it's a line. If I have a 3D data, then the linear decision boundary would be a hyperplane. Like it will be a plane for more than 2D, it's going to be a hyperplane. Okay. So now depending upon whether I can draw a linear line or linear decision boundary to classify the problems, we are going to divide problems into 2 types. So one is linearly separable problems, which are easy to solve problems because you could just use a linear classifier like a linear model and you could solve it. An example for linearly separable problem is exactly what we have seen before. So this is basically you have a bunch of circles and cross and you need to classify this. So drawing a linear line is sufficient. Okay. And we also have problems which are not linearly separable. In fact, most of the real life problems, most of them are not linearly separable. Okay, so to give an example, so here is the same circle and cross problem, but let's say my data set looks something like this. Okay, so now this is my data set. So how do I draw a boundary between these two classes? So one possible boundary is this, right? So now this boundary is not a linear line. So this is non-linear. So these problems are not linearly separable. Okay, so maybe we will stop here. I will take few questions and we could continue discussing more about linear classification in the next lecture. Any questions before we stop the recording? You could raise hand. Masood?
Just a question. So how should know which one of these, I mean, generative, discriminative, and the other model prediction? How we should know which one is we should use when it's based on the
Okay,
model?
so well, that's a very deep question and probably okay. It's a hard question to answer and like but we will have a discussion, at least a discussion about this question after we introduce some example algorithms for all these 3 approaches. So maybe in few weeks. But please remember the question and like we will discuss this in detail in one of the lectures. Okay. Any more questions? Okay, there's a question in chat. So how do you go about finding P of X given CK and P of CK in practice? Well, we will answer this question in the future lectures. So we are going to discuss about how to find P of X given CK, how to find P of CK, how to find P of CK given X, like how to find F of X, everything in the next few lectures. Okay, there are a couple of hand raises.
Another question. So, sorry,
okay.
In non-linear example here in the slide, is it possible to use multi-linear instead of a non-linear? I mean, instead of, for example, in this special, in this specific example, can we use 2 linear classification instead of a degree 2 polynomial, for example?
Well, if you use a degree 2 polynomial, yeah, I think a degree 2 polynomial would fit this perfectly, but that is not a linear decision boundary. So that is not that's a non-linear decision boundary. Yeah, you have to use a degree 2 polynomial if you want to fit this. Okay. Any more questions? Okay, so there is some question about assignment in Piazza, which is not answered. Okay, I will check with the TAs. Hopefully they will answer it soon. Okay, so linear classification means the boundary is linear. That is right. So when I say linear classification, okay, maybe I did not formally define what is the linear classification. So it's like I just mean that like I'm using linear models for classification. So they could have only linear decision boundaries, but we have also seen a hack to make them non-linear decision boundaries, right? Like, so you take a linear decision, like linear model, add non-linear basis functions to it, you're going to get non-linear decision boundaries. So any linear classification model that we are going to discuss in this course, you could make them non-linear easily by just adding basis functions. Okay, so I think I will, okay, so there's one more question. Are there any difference between the features and the parameters? Yes, they are very different. So let's consider the simple regression model, right? Like, so where the y is given by w0 plus w1x y hat, right? So now these w's are the parameters of the model, which are something that you're learning. On the other hand, x is the feature that is given to you. Okay, so I will actually stop the recording here.